By the early 2000s, the European Space Agency, ESA, was ready to make its mark on the global space stage. While NASA, the Soviet Union, later Russia, and China had made significant strides in space exploration, Europe had not yet launched its own lunar mission. In 1999, ESA decided to develop its first lunar probe, SMART-1, with a clear goal in mind: to explore the moon and test new technologies that could enhance future space missions. The idea behind SMART-1, smart exploration of the moon and planets, was not just about science. It was also about proving that Europe could develop cost-effective, innovative space technologies. With a limited budget compared to NASA or Russia, ESA needed to think outside the box. The choice of using electric propulsion, a more fuel-efficient method for space travel, was a bold decision that would later become one of the mission's defining features. This was a crucial turning point for Europe's space ambitions. Launching a mission to the moon meant proving to the world that ESA was capable of conducting sophisticated space exploration, not just in the realm of satellites, but also deep space missions. The SMART-1 mission faced its share of challenges right from the start. Developing a spacecraft that could orbit the moon, gather scientific data, and return valuable information to Earth was an ambitious task for ESA, which had limited prior experience in deep space exploration. The main innovation of the SMART-1 mission was the adoption of ion propulsion, a form of electric propulsion that uses electrical energy to accelerate ions to high speeds. This technology would save on fuel and provide a more sustainable way to reach the moon. However, using ion propulsion came with its own challenges. Unlike traditional chemical rockets, ion propulsion operates with lower thrust and takes much longer to reach its destination. This required careful planning and a novel approach to space travel. Additionally, ESA had to ensure that all the spacecraft's instruments, including a miniaturized X-ray spectrometer and an infrared spectrometer, were designed and calibrated precisely. Any malfunction could jeopardize the mission's scientific goals. These challenges were compounded by the fact that SMART-1 was not just a scientific mission, it was a demonstration of Europe's space engineering capabilities. On September 27, 2003, SMART-1 was launched aboard an Ariane 5 rocket from the European spaceport in French Guiana. The mission's launch marked a significant moment for Europe, as SMART-1 was the first spacecraft developed by ESA to journey beyond Earth's orbit. The mission was unconventional in some ways. Instead of taking the typical, fast route to the moon, SMART-1 used a technique called low-energy transfer, which took advantage of the gravitational forces of Earth and the moon to gradually propel the spacecraft toward its destination. This method allowed SMART-1 to use less fuel, but it meant the journey would take longer, over a year. It was a bold risk, and the European team had to ensure everything worked perfectly over an extended period. As SMART-1 began its long journey to the moon, ESA engineers and scientists at Mission Control faced a constant pressure to keep the spacecraft on track and ensure the ion propulsion system functioned as planned. The next challenge was ensuring the spacecraft's instruments operated effectively once it reached lunar orbit. The mission had just begun, and there were many hurdles still to come. After a long journey of about 14 months, SMART-1 finally entered lunar orbit on November 15, 2004. The spacecraft's first task was to begin mapping the moon's surface and studying its mineral composition. The arrival at the moon marked a significant achievement for ESA. SMART-1 had completed a journey that had tested not just its propulsion system, but also Europe's capability to undertake complex interplanetary missions. Despite the slow approach to the moon, the ion propulsion system performed beyond expectations. SMART-1 had entered a highly elliptical lunar orbit, which allowed it to conduct scientific observations from varying altitudes over time. The spacecraft's X-ray spectrometer was particularly effective, allowing it to observe the composition of the moon's surface in ways that hadn't been done before. While the scientific data was being gathered, the mission faced a constant threat of space weather and technical malfunctions. The harsh environment of space, with radiation, extreme temperatures, and micrometeoroid impacts, was a constant challenge. The spacecraft had to operate for an extended period, and each day brought new risks. Part 5. Scientific Breakthroughs and Discoveries. Despite the challenges, SMART-1 made some important discoveries. The X-ray spectrometer helps scientists identify the moon's mineral composition, giving insight into the composition of its crust and helping to identify new areas of interest for future exploration. The mission also helped map the moon's surface in greater detail, which was essential for planning future landings and resource exploration. Perhaps the most significant achievement was the ability of SMART-1 to observe the moon's polar regions, where the lunar environment was largely unexplored at the time. The spacecraft detected traces of water ice in the permanently shadowed craters at the moon's poles, a finding that would become critical for future lunar missions, including NASA's Artemis program. The use of electric propulsion was another key breakthrough. The spacecraft's ability to reach the moon and conduct scientific observations with such minimal fuel consumption was an achievement in space efficiency. This technology would play a significant role in future deep space missions, including interplanetary exploration. Despite the challenges, SMART-1 made some important discoveries. The X-ray spectrometer helped scientists identify the moon's mineral composition, giving insight into the composition of its crust and helping to identify new areas of interest for future exploration. The mission also helped map the moon's surface in greater detail, which was essential for planning future landings and resource exploration. Perhaps the most significant achievement was the ability of SMART-1 to observe the moon's polar regions, where the lunar environment was largely unexplored at the time. The spacecraft detected traces of water ice in the permanently shadowed craters at the moon's poles, a finding that would become critical for future lunar missions, including NASA's Artemis program. The use of electric propulsion was another key breakthrough. The spacecraft's ability to reach the moon and conduct scientific observations with such minimal fuel consumption was an achievement in space efficiency. This technology would play a significant role in future deep space missions, including interplanetary exploration. In 2006, SMART-1 had completed the primary goals of its mission, but it continued to gather valuable data. However, ESA knew that the spacecraft fuel supply was running low, and the end of the mission was approaching. On September 3, 2006, after nearly 2 years in lunar orbit, ESA decided to end the mission by intentionally crashing SMART-1 into the moon's surface. The crash was planned so that the spacecraft would fall into a remote region of the moon, where it wouldn't interfere with future missions or lunar operations. Before the crash, the spacecraft continued to send back valuable scientific data, and its final moments were a fitting end to a groundbreaking mission. While SMART-1's end was bittersweet, it marked the successful completion of the mission, demonstrating that Europe had the capability to not only reach the moon, but to gather meaningful scientific data as well. Although SMART-1 may have been a smaller mission compared to those from NASA or Roscosmos, it had a lasting impact on Europe's space ambitions. The mission demonstrated that ESA could undertake successful lunar exploration, even with a limited budget, and helped pave the way for future European deep space missions. The lessons learned from SMART-1, particularly in the areas of electric propulsion, lunar exploration, and cost-effective mission design, continue to inform ESA's current and future missions. It inspired more ambitious missions like Rosetta, which would go on to land on a comet, and ExoMars, which is part of a joint mission with the Russian Space Agency to search for signs of life on Mars. SMART-1 also helped establish the moon as an important destination for European space exploration. The Lunar Gateway, a collaborative space station orbiting the moon, is one of ESA's future projects that draws on the lessons learned from SMART-1. As the first European mission to the moon, SMART-1 remains a cornerstone of ESA's deep space exploration program and a symbol of Europe's growing role in space science and technology. Conclusion: the SMART-1 mission demonstrated that European ingenuity, even with limited resources, could achieve extraordinary feats in space exploration. From its use of innovative electric propulsion technology to its scientific discoveries about the moon's surface, SMART-1 helped Europe take its first significant steps in lunar exploration. The mission's legacy continues to influence ESA's current and future space endeavors as Europe continues its ambitious journey beyond Earth's orbit.